Look here, if we know the radius of a circle, we can immediately calculate its area, since the area of a circle is equal to pi r squared. In this formula, pi plays a key role. But there comes a question. The history would go a long way before Archimedes in ancient Greece calculated pi to 3.14. So what about the times earlier? How did the Asians calculate the area of a circle? Some people might think, well, I could just cut the circles into squares like this and add them up. Well, there would be some errors. But come on, it was the Asians. They were probably just calculating the area of a pizza. So why the need for such precision? Well, we shouldn't underestimate the Asians like this. They were not that foolish at all. In fact, as early as more than 5,000 years ago in ancient Babylon, people began to calculate the area of a circle in this way. First, wrap a string around the circle to measure the circumference c, then straighten the string to measure the diameter of the circle, and then calculate the circumference multiplied by the diameter divided by 4, which yields a fairly accurate value for the area of the circle. However, this was just an empirical method. The ancients used it, yet they couldn't explain why it worked. It was not until ancient Greece, when human logical thinking suddenly boomed for some inexplicable reason, that Archimedes, a legendary mathematical giant of antiquity, provided a proof. Archimedes said, "Oh fellas, let's first cut a circle into 4 pieces and then put them together. Look, we got a sort of, well, odd shape." Well, the shape is not pretty, but we clearly know that the sum of its top and bottom sides is circumference of the circle, and the sum of its left and right sides is diameter of the circle. What if we cut the circle into 6 pieces and assemble them? It looks like this. 8 pieces, this is what it becomes. 10 pieces, here it is. We keep cutting and keep assembling. In fact, we don't need to cut it into too many pieces. When we cut it into 100 pieces, the shape formed by assembling them is already very close to a rectangle. Naturally, the sum of the top and bottom side of this rectangle is still the circumference of the circle, and the sum of its left and right sides is still the diameter of the circle. So we can directly calculate the area of this rectangle, which is the circumference multiplied by the diameter divided by 4. And that is exactly the area of the circle. Looking back now, Archimedes' proof already had the rudiments of modern calculus. It was like a seed zone, but after falling to the ground, this seed lay asleep for 2,000 years, with no one perceiving the enormous power hidden within it. It was not until 1665 that another giant picked up this seed and thought, it is time to do something. In 1665, a plague swept across Europe. To escape the plague, people fled to countryside. Cambridge University closed its doors for a break, and students were told to go home, including a 22-year-old student named Isaac Newton. Newton's home was right in the countryside, so he was in a quite good mood after returning. In the evenings, he would sit in the yard and gaze up at the starry night. At that moment, a song came to his mind, which sang, "Look into the moon." No, Newton had never heard of this song. What actually crossed his mind were the first 2 of Kepler's 3 laws. The first law states that the orbit of a planet is an ellipse. The second law states that a planet orbits an ellipse sweeps out equal areas in equal intervals of time. Kepler proposed these 2 laws in 1609. Yet his derivation relied entirely on observation data. In other words, these 2 laws were initially just empirical conclusions and had not been rigorously proven. Newton then thought, is there a way to verify them? However, this involved 2 calculations that were completely impossible at that time. First, a planet moves along an elliptical orbit. How can we calculate its speed at any given moment? In classical math, we can calculate the average speed of an object, subtract the initial position from the final position, and divide by the time elapsed. Even for a circular orbit, we can assume the planet's speed is a constant and roughly calculate an average speed. But this formula is completely inapplicable to an ellipse. Obviously, the planet's speed changes at every point on the ellipse. So what should we do? Well, Newton thought, what if we still calculate the planet's speed the same way as we calculate the average speed? That is, connect the initial and final position, calculate the straight line distance between them, and then divide by time. But obviously, this would lead to a huge error, because the planet travels along a curve, while we calculate a straight line segment. But it doesn't matter. Let's gradually move the starting point closer to the ending point. When they coincide, we calculate the instantaneous speed. We use a capital S to represent distance and t for time. Newton's calculation is essentially what we now call the derivation, though Newton named it the fluxion. Now let's turn to Kepler's second law. A planet sweeps out equal areas in equal times. So another question arises. Given a period of time, how do you calculate the area swept by a planet? Newton looked up at the starry night again, and another song popped into his head. Okay, no more jokes. After research, Newton discovered that the fluxions we calculated earlier could actually be used to calculate the area. This is the extremely important fundamental theorem of calculus, which in modern mathematical terms is expressed as follows. Calculating an area and calculating a derivative are exactly inverse process. This is what we call integration in modern mathematics. Using integration, we can calculate the exact area swept by a planet in a given time. Okay, how Newton deduced the law of universal gravitation. In the universe, the space between celestial bodies is almost a vacuum. So for people in Newton's time, it was logically reasonable that celestial bodies should move in a straight line. Newton initially made this assumption too. Suppose a planet is indeed moving in a straight line and travels from point A to point B in a certain time. According to the principle of inertia, in the absence of external forces, it will move to point C in the next interval of time. If we take point O as the reference point, these two triangles have equal bases and same height, so their area are equal. In other words, if the planet moves in a straight line, Kepler's second law naturally holds true. Strangely enough, however, the actual orbit of a planet is like this. How to explain this bizarre phenomenon? There seems to be only one possibility. The planet is pulled by some mysterious force from point O. But for Newton's contemporaries who had not yet developed a calculus brain, this explanation still did not hold, because if the planet is pulled by a force from point O, that force must act along the straight line OC, pulling the planet to point D. We already know that the area of OBC is equal to that of OBA, so the area of OBD must not be equal to that of OBA. Thus, Kepler's second law would not hold, and all observational data would be wrong. But Newton said, fellas, don't worry, because we know the planet's orbit is an ellipse. We cannot take this delta t as a large value. Instead, we must treat it as an infinitesimal. When delta t approaches 0, the line OB is essentially stationary. Therefore, the pulling force does not act along OC, but along a line parallel to OB. So the subsequent point D is not here, but should be right here. Now, since CD is parallel to OB, we once again have two triangles with equal bases and equal heights, and their areas are equal once more. Thus, the area of OBD is equal to that of OAB, perfectly conforming to Kepler's second law. Therefore, this pulling force from point O does exist. Let's call it the universal gravitation. So we see, universal gravitation was a hypothesis from the very beginning, and we could have just as well made a different one. For example, Einstein later proposed an alternative hypothesis. He said we don't need gravity at all, as the curvature of space can explain celestial motion perfectly well. Perhaps in a few decades, we can come up with another hypothesis. For instance, We could say that we need neither gravity nor curvature. Everything in the universe is just the thermal expansion and contraction following the Big Bang. Surprisingly, this seems to explain everything too. Alright, let's get ready to win the next Nobel Prize. That's all for today. Thank you all.